This is the world's sneakiest substitution. The Weierstrass Substitution. It was suggested in James Stewart's calculus that Carl Weierstrass was the first one to use this clever substitution that takes rational functions of sine and cosine and turns them into ordinary rational functions of t, making them easier to integrate. Unfortunately, he wasn't the first one to do this. However, it now bears his name. So we begin with letting t equal the tangent of theta over 2, the half angle of theta. We then construct a right triangle using theta over 2 as our angle, and the tangent being the opposite over the adjacent, we make it t and 1. We find the hypotenuse to be the square root of t squared plus 1. This allows us to write expressions for sine of theta over 2 and cosine of theta over 2 in terms of t using this triangle. Next, we're going to employ some double-angled formulas for sine and cosine. Namely, sine of 2 alpha is equal to 2 sine alpha cosine alpha, and cosine 2 alpha is equal to cosine squared alpha minus sine squared alpha, where alpha is going to be our theta over 2. Therefore, 2 alpha is equal to theta. Making this substitution, the sine of theta works out to be 2 multiplied by t over radical t squared plus 1 multiplied by 1 over radical t squared plus 1, and that works out to be 2t over t squared plus 1. Using the double angle for cosine, we get cosine theta is equal to the rational expression for cosine squared minus the rational expression for sine squared. Simplified, that gives us 1 minus t squared over t squared plus 1. Next, we take the expression that we just got for sine of theta, and we're going to differentiate both sides of that so that we can get expression for d theta. And with a little help with our either quotient or product rule, however you like to use the differentiation rule here, we get d theta is equal to 2 over t squared plus 1 dt. So now we're ready to make some substitutions into our original integral. So our original integral from 0 to pi over 2 of 1 over 2 plus cosine theta d theta, we make the substitution for cosine, making it 1 minus t squared over t squared plus 1. The substitution for d theta, which is 2 over t squared plus 1 dt, and we multiply through with the denominator there. Now for the limits of integration, we're going to change them, so from 0 to pi over 2, they now become 0 to 1. And cleaning up this expression here, we get the integral from 0 to 1 of 2 over t squared plus 3 dt, a much nicer integral to work with. So now, because of this integral looks very familiar, it looks a lot like the integral that gives us the arctangent, we're going to work towards making it look like that. So we're going to make a substitution of u equals t over radical 3, so that u squared is t squared over 3, and you'll see why in a minute. So taking our integrand and multiplying both the top and the bottom by 1/3, essentially a fancy form of 1, on the top we'll get 2/3, and on the bottom we'll get t squared over 3 plus 1. Now you'll see why this u substitution makes sense. Making the substitution into our integral, we get the integral 2/3 multiplied by 1 over t over radical 3 quantity squared plus 1 from 0 to 1. And with the u substitution, we can also make a change of the limits of integration here from 0 to 1, and that's going to go from 0 to 1 over rad 3. Pulling that 2/3 constant out, we're going to simplify our integrand here. And the differential we'll need here is differentiating the equation for u with respect to t. We get radical 3 du equals dt. So plugging that into our integral here and pulling out that constant of the square root of 3, we get 2 radical 3 over 3 multiplied by the integral that would give us the arctangent evaluated at its limits, really the arctangent of 1 over radical 3. So we get 2 rad 3 over 3, and the arctan of 1 over rad 3 evaluates to pi over 6. So we clean that up a little bit, 2 pi radical 3 over 18, or pi radical 3 over 9. Now if you caught my last video, you might notice that this is very similar to the answer we got there. You see, the integral here is pi radical 3 over 9. And that integral is exactly half of the integral from 0 to pi over 2 of the cube root of tangent over sine plus cosine squared d theta. And that integral was the integral from the MIT Integration Bee 2023 Finals, problem number 1. And again, if you're interested in seeing how that one was solved, check out my last video. Pretty neat, huh? Well, that's it for now. Thanks for watching. Please like, hit that notification bell, and subscribe to my channel, and I'll see you on the next one. Stay tuned.